We're going to start the core scanning technologies session offered to us by CoreLift, so we're happy to have that going. The third talk of this session is going to be addressed by Simon Lessard. Simon is the co-founder of LithologIQ, specialized in real-time hyperspectral core scanning for the mining industry. With 16 years of experience in hyperspectral products development and a background in electrical engineering, he brings deep expertise in infrared imaging techniques. Recognizing a gap in mineralogical data delivery, he helped develop a faster, more reliable solution. Passionate about innovation, Simon focuses on connecting advanced technology with field operation to accelerate exploration and mining decision-making. Today, Simon is going to talk about accelerating mineralogical insights using VNIR, SWIR, medium wavelength infrared hyperspectral core scanning. Simon?
Thank you very much, Gervais. Thank you very much, everyone, to accepting to spare 2 minutes of your time. Okay, so I've been asked a few weeks ago to present our results. Yeah, it was pretty quick. Regarding hyperspectral drill core scanning. So I put a few slides from some projects we've been realizing in the last couple of years. Each of those 3 case studies will present a different aspect of the results we've been generating at our different sites. So before I jump in, very quick overview of what is hyperspectral imaging to make sure we start all on the same base. So hyperspectral imaging is a technique that measures continuous spectrum all over the sample area. When I mean continuous, when I say continuous spectrum data, it starts from the RGB up to the long wave. So different combination of sensors can cover this wide spectral range, but it is continuous. So it ends up as a result that you get a full image of the sample, the core, for example, where at every millimeter square, you have the full spectrum. And so you can do spectral analysis on those pixels and recover mineralogy. So it can be multiple minerals at the same pixel. So with unmixing, you can extract many mineral maps from those pixels. So the basic characteristic is that it's non-destructive, it's fast, it's light on sample preparation. Of course, it cannot be covered with thick layer of muds or a big debris or water. That's a surface measurement, of course. But it's still very tolerant to surface or weathering of the core. Yeah, the main characteristic is the speed and ease of calibration and core sample prep. It's also very tolerant on different type of samples you're scanning, split core, full core, chips. It's easy to deploy. So what it is, where does it thrives? When time-sensitive workflows are in place. So in an active drilling projects, having a lot of drilling daily where results are really critical to have in a very short time. It can provide real-time insight in these cases, as well as in operation when short-term management requires planning based on grade control or geomet parameters acquisition, so it can really provide quick turnarounds to control these parameters. What it is not, it's not replacing the assays, so it can limit, it can optimize the assay selection, but it's not going to replace any assay results. And it's not performing very well in case of sulfide minerals. So sulfides are pretty flat in terms of spectral response. So I know that some people are using RGB to extract the sulfides. That's a possibility. Or if sulfides are bigger than a pixel, so bigger than a millimeter square, using that flat line, well, that's some kind of information we can use to infer the presence of sulfides, but disseminated sulfides remains a challenge. So here, that is the exact system that was used in the 3 case studies I will present in the next slide. So this is a mobile core scanner, including 6 different sensors, so 3 hyperspectral cameras, one visible range, visible near, getting iron oxides and rare earth elements oxides. Shortwave for hydrated minerals, it basically lock into the OH bonds of the minerals. So those are the main 2 common spectral range that you will see in PIMA, you will see in TerraSpec or in most core scanning technology. Those are the most common found. One that we have here, and it's in the focus of the presentation today, that is the midwave hyperspectral camera, still in imaging mode. So you're getting the full image of the core using hyperspectral scanning. So it's really strong in picking the carbonates. And I know we can get the carbonates from the shortwave. Some people are using it for it. But with the midwave, we get a much lower level of detection, up to a few percentage of carbonates, even in disseminated carbonates, and carbonate chemistry as well. And recently, we've demonstrated the ability to pick up the silicification using the midwave as well, so we can map the quartz as well. Then high resolution RGB camera, taking the wet and dry, magnetic sensibility, as well as UV fluorescence. That is all included in this piece of equipment. So guess video will run. So everything is automated. One guy put the box on the conveyor. So you see everything is conveyor based. So it's fairly easy to attach to any workflow, including conveyors. So you can stack multiple boxes. Box will be detected and fed automatically in the machine, and the scanner will scan inside the trailer. It will go on under those 6 different sensors, and in 1 minute, the core will be out on the other line. So it's really a continuous process. During this presentation, you will hear a lot about workflow, about speed, and this is really the angle we are attacking in this, I would say, crowded core scanning market. And you will understand why during the presentation. I think that's really important to bring this technology as fast, as easy to use as possible, and as real time possible to really tap on the benefits of what it can do. So when it's scanned, it's processed on the machine on site, so data will never leave the sites. And the results then is pushed back on a portal like this, so you can customize the view. You can put side by side the different mineral maps, the different chemistry maps, mineral chemistry maps. You can even load in your assays or your lithology, so you can have everything side by side, navigate your project and see how does everything correlates together. And this is how we actually deliver the results to the customer. So this dashboard ends up right on top of the core table. So the geologist have a look at this. He's having his core in front of him, and it can provide insights, support his mineralogy, support his logging, and help him focusing on what are the most priority zones to work on based on what the software has identified. So now the case studies, let's jump in the crunchy part. First one, Eldorado Gold, Quebec. It's a project we've done since 2024. The context of that is that it's a structurally controlled greenstone holds the gold deposit. The gold is associated with different alteration from carbonate, white mica, chlorites, and some sulfidation as well. Alteration, mineralogy and chemistry track the fluid pathways controlling the mineralization. So this project was an ongoing drilling project. So a core were drilled every day, and we were asked to follow the pace and provide really quick insights to support active logging. So they needed a consistent logging of the alteration to properly drive the exploration project. So having the challenge of consistency across logging, so multiple geologists were logging at the same time. Inconsistency, well, it's not surprising. Alterations are difficult to see with the naked eye, so that was one of the challenge. Backlog was also happening quite often because the amount of core that was delivered every day. People had challenges in following the pace and to resolve those cryptic alteration and carbonate chemistry visually with the actual tools. So the objective of the project, so why did they ask us to come and to demonstrate our technology, was to first, in the first phase, demonstrate the ability to generate valuable data. So how this data is actually accurate, and it helps, it provide answers to the logging activities. So that was the phase one, where we did 10,000 meters of scanning in 2024. So it was really about validating the data quality. The phase two, last spring in 2025, we scanned 25,000 meters over 2 or 3 months, about that. And this time we were involved actively in the workflow. So first time we were kind of aside just to demonstrate the quality. Then the second time we were in the workflow. So cores were delivered in the morning. We had a couple of hours to scan them, and results were required by the next day, 8 a.m. Very strict about that because that's what was the support for the log for the geologist. And the rest of the day we were scanning historical core. So we have plenty of capacity with this with the scanner at the speed we scan. So we were just digitizing the old historical core from the core yard. So so why this technology was selected for the test? It's well, because mainly it can automate many different measurements that people are doing manually. So contributing to the backlog they were the backlog they were experiencing, like wet and dry photography. So people can do it manually, right? But it takes time, and if you can automate it, everybody wins. Maxos, the same thing. And the spectral range we were covering, including the mid-wave, that was one of the key arguments in selecting this technology because of the mid-wave resolving the carbonate chemistry. So the mid-wave capability here, because of this ability to map the carbonate mineralogy and carbonate speciation, this was really something that was expecting to resolve some of the logging issue and discrepancies in different logging. And the operational performance, that was another reason for this technology because of the high throughput. One of the challenge and the goal was to resolve this backlog. So having this capacity to process that many core per day, there was really hopes in being able to solve the problem. So regarding the results now on the operational side of thing, so we were able to process those fresh core and deliver by 8 a.m. every morning, about maybe 9.9 time of the day, every day. So it was really demonstrated. We peaked at 1,400 meters of core scanning per shift, about eight hours. So that's the rate we got, and so it was more than enough to support the actual drilling project and scan a bunch of core from the historical logs as well. And a successful integration into the workflow. So given the configuration, so cores were delivered, scanned, and quickly returned to the logging table. So we were not disrupting the logging workflow for the geologists. So geologically wise now, what are the outcome? Robust alteration mapping. So I think we kind of solved this visual alteration challenge they have. Carbonate mineralogy using the mid-wave and carbonate chemistry as well was accurately mapped. We could have had quartz mapping in the bunch here, but at this time when we did the project, the quartz processing from the mid-wave camera was not ready yet. So now it is. We are reprocessing, but as it was mentioned earlier, it can be done using the shortwave, but that's mostly the hydration that we measure, so it's not that reliable. But using the mid-wave, quartz is really, really reliable. So it will be added to the list of what we've delivered in anytime soon, plus highlighting some mineralization that was not really visible by the human eyes, like diorite dikes that were overlooked in this project. So lesson learned. We were hoping that we would really accelerate the logging during this project, but it turns out that it was a little bit slower because we were giving so much more insight information to the geologists, so they were taking more time in looking at small details that they were not looking before. But I really think it can be improved over time as both the core scanning vendor and the customer learns how to use this, and maybe reports can be adapted, so we put some distraction aside and geologists learn how to focus on what is relevant and leave those extra details aside. So there are great hopes that, and it was demonstrated anyway with other projects, that eventually core logging will become much faster. Productivity increased over time, so that 14,000 meters we peaked at, well, it really increased as the project we were moving on, because everybody was learning how to have this operating workflow. But it takes time. It will take time to everybody to really embrace this technology and accelerate it. Next case study, it was at Wisdom. That's a reduced felsic intrusion cutting metasedimentary belt. So basically, there is a low sulfide content, and gold is controlled by fine grain mineral zoning. Alteration intensity was again very tough to track. And this might lead, because of the presence of some minerals we identified here, it might lead to metallurgical challenge here, because the ore has a great variability that is driven by gangue mineralogy. And subtle mineralogical changes strongly influence the recovery and the froth behavior and the reagent consumption as well. Especially when we are looking about on the talc, because in this project, talc was located almost everywhere in the zone or out of the zone. So it was really difficult to see exactly have a great control over the geomat process. So it's problematic because talc is not resolved by traditional logging of the core or traditional geochemistry methods. So it was like processed without consideration of the talc. And what you see on the graph, the red is the talc that we were mapping, and we can see it's almost everywhere inside or outside the mineral zone. So it has strong geometallurgical implication regarding the recovery and the froth instability. So this is something that we mapped pretty nicely with the SWI, the short wave, using the OH bond. So we were able to track and map the talc independently of the gold mineralization. So this can be provided as an insight, so to predict what would be the efficiency of the process, rather than, well, getting the results when it's done and trying to find why was the recovery bouncing up and down. Using the mid-wave quartz were detected in this project, and carbonate discrimination and speciation was also achieved, as we can see on the left. The last color column, I would say the fifth from the right, from the left, sorry. The blue and green is the actual carbonate chemistry. Then we have the chlorite, and the first one is the talc, and some tourmaline veins as well were mapped on this project, all correlated to the gold grades. So the key outcome for this project was really upfront assessment of potential metallurgical issues, mainly driven by the talc. So it can be a support for proactive blending strategies or reagent optimization or froth management planning. So yes, that's it for this one. And the last one, case study number 3, free gold. That one is looking at the different angle, really about sample selection based on an alteration index. So that was a fairly small project. It was about 6,000 meters outdoor in a shelter in very bad condition, weather. It was last fall, so it was snowing and everything, but still we did it anyway. So it kind of put our equipment to good testing in those conditions. So the geological setting here is gold mineralization associated with sulfide subtle alteration. And those subtle alterations were kind of tough to see with the naked eye again. And it led to maybe missing some zone for sampling or oversampling in other zones. So in this case, the alteration index, which is the third column, the yellow one here, that we can see on the graph. And the last one is the gold. Gold is coming from traditional assay tests. And the previous one is the alteration. So what we can see is the alteration score that we generate based on here. What was the mineral? I think it was white mica, tourmaline, and chloride potentially. This alteration score tracks pretty nicely the mineralized zone. So we can use this as a tool to do sample selection or to vectorize or just to prioritize the geologist's work in logging the zones where the score is the higher. So once it's trained, this score is produced like on a regular basis. It's delivered in real time at the same time as the mineral maps. So it really support active logging work. So yeah, it can lead to decision for drilling. So should I stop or continue drilling? Am I hitting a new mineralized zone? So maybe should continue drilling or stop or change the next drill hole location. So this is the kind of benefits it can bring. Oh yes, I have here. So yeah, tourmaline, white mica, and talc were used for defining this alteration score. And regarding the tourmaline veins, they were really fine in this project. So sometimes they are just not logged at all. They are overlooked because they are too fine or difficult to see. But with the hyperspectral, we logged them pretty nicely. So in this project, the alteration score was really the key element, and it was mapping 87% of the mineralized zone. We've seen project. We saw project with higher score. In this case, it was 87. We've seen up to 95, 98% of correlation. But the project was pretty small, so we didn't have a very wide training data sets and, well, harsh condition with wet and frozen core. It certainly didn't help, but still it was pretty accurate. It highlighted the small tourmaline veins and stuff that were overlooked. And here, one thing that is interesting regarding sample selection, if you look at the graph, the 100%, the highlighted zone, it is what we would have recommended as the sampling. But if we look at about the 12 or 15 drill holes here, and what was done as a sampling, every bar, black bar that goes up over 100% is oversampling, and everything that is below is undersampling. So there were indeed some missed zone that were undersampled and some zones that are oversampled. So in one case, that's maybe overspent money on some tests, and in the other case, maybe missing mineralization zones. So this tool can really help optimizing the sample selection. And eventually maybe adding the MG-rich amphibole to refine this alteration score. Maybe we could probably crank a little percent on top of that. So conclusion here, our vision regarding core scanning, so we are well aware that there are many core scanning technologies and different vendors in the space, but we have this vision that core scanning must be really fast. It must be brought to real-time core scanning. It must be simple enough to use and to maintain calibration so it becomes a commodity. And it's fast enough so people won't cherry pick anymore the core that they will scan, because that induces some kind of bias into the sampling, and it's exactly the purpose of that technology. So if we bring this technology down to a level, it's cost effective enough, it's cheap enough, and it's easy enough, and it's not the bottleneck of any operation, I think that it just becomes a regular tool for the geologists, so another tool they have in their tool set to perform their core logging. And once we've reached that level, I mean, that it will become a no-brainer that the logging will be machine-made, and the geologists will have their brains spent on other tasks rather than again logging, but more in interpretation and controlling the logs. So real time, it's really the key here. And real time, we can scan up to 2,000 meters of core, but of course nobody drills that many core per day. But the key is that every box scan in 1 minute, so no geo will wait for the results. So it won't disrupt any workflow. So if they scan like 500 meters per day, that's perfect. They will have the results by noon, and things continue for the rest of the day. So yeah, that's about it. That's where we stand regarding core logging. Now it's hyperspectral, but we are connecting many other technologies that you might see some future announcement in 2026. We have other technologies that will complement what we are currently doing with core logging. So I think we will have a pretty nice Swiss knife technology in the coming year. Thank you.
We have time for a few questions, one or two, and then we'll go to the panel discussion afterwards. Yes?
Santiago here. Hi, Simon. Thank you for your presentation. It was really good. My question is regarding the processing, because you made the point clear that you want it to be real time. So the processing, is it in situ processing, or is there a need to upload the data? If so, what's the turnaround time to get that data back? Because you mentioned also the project that you had no connectivity. So if you can explain a little bit more about that. Thank you.
Yes, of course. Thank you for the question. So the processing is done on board on side of the machine. So all the computers are integrated into the scanner. So 1 minute to scan the box, approximately 1 minute to do the processing as well. Then the result, which is much lightweight, much lighter, then this one can be uploaded to the cloud or delivered locally as well.
One more question? Brian?
Can you comment on the UV outputs that your scanner provides? Is it images or does it?
The UV,
Yeah.
the fluorescence?
Yeah.
Yes, of course, that is a UV light that we shine on sample, and we collect from the RGB cameras with some special filters. So that's not a UV camera, that's UV illumination shining, is triggering the fluorescence. So we've done some projects in lithium. It can make some spodumene shine if they have these manganese impurities. So it can be a very efficient and cheap and fast technology for lithium exploration if there is this manganese impurity. But other than that, honestly, at this point, we are developing applications for the use of UV fluorescence. Some calcite, some other minerals are fluorescent, but it has to be developed and tried to better understand what is the actual application for this.
Thanks.
Thank you.
Thanks, Mo. Thank you.